Alright, so we are going to do numbers 2, 3, and 10 on Skill 1 under Chapter 11. Feel free to fast forward or rewatch if you need to. If you understand how to do these problems, then go find some that you don't, and I'm going to try and do one of each. So let's go ahead and start off with number 2. It says, which of these materials is polar? It might not be evident just by looking at their chemical formulas. So what you would want to do is go ahead and draw out their Lewis structures. Since we've already done that in a previous chapter, I'm just going to go ahead and show you their Lewis structures, and then we can talk about which ones look polar. Alright, so here they are. Remember the formula. Some of these, like this one and this one, could be looked at as exceptions, so you don't necessarily have to do the formula. So P2H2 looks like this, PCl3, BrF5, C6H6 is a little complicated to draw. It requires a ring structure. I wouldn't be too worried if this wasn't evident that you needed to put it in a ring structure. I don't think it'll be that tricky, but you can see it required 15 bonds, and so I made it into a ring. And then we have CH3F. So the answer you already know is 1, 2, 3, and 5. So I just want to look at the ones that might not have been as clear as why they're polar. So on numbers 2, we have this extra lone pair. And on number 3, we have this extra lone pair on the center. That makes them polar. On number 5, it looks tetrahedral, so it doesn't quite look like it would be polar. But remember, if all the outside atoms aren't identical, the structure is going to be polar in this case. Fluorine pulls electrons differently than these 3 hydrogens. So our final answer should be C. 1, 2, 3, and 5. This ring structure that we drew is equal. All the electrons are shared equally. Alright, so number 3. How many of these statements about lattice energy, and lattice energy is only going to be found on ionic compounds, are correct? So look over here, all of these are ionic. And so each statement is just comparing 2 ionic compounds. So let's start with the first statement. Sodium fluoride has a higher lattice energy, than sodium bromide. So the first thing I'm going to check are the charges. So we have a 1, a 1, a 1, a 1. That doesn't really help us. So remember, we want high charges but low radius, small radius. So if you go to your periodic table, we don't really need to compare sodium and sodium. Those are constant. So if you want, you can just kind of cross that out and make it easier on you. So what has a smaller radius? Fluorine or bromine? Fluorine does. Fluorine has smaller radius. Because it has a smaller radius, that means it has a larger lattice energy. All right. So does that statement make sense? Sodium fluoride has a higher lattice energy? Yes. All right. Let's go to the next one. So I'm going to check out the charges. We have 2 and 1. Doesn't matter how many you have of them. We're just going to write the normal charges. 2 and 1. So again, charges aren't really going to help us out. They both have magnesium, so I'm going to go ahead and cross that out. And now we're thinking about fluorine and bromine. Well, we're in the same scenario as the first statement. Fluorine has a smaller radius, therefore it has the largest lattice energy. Does that make sense? Yes. For lattice energy, we went small radii and big charges. So on the next one, we have calcium oxide and calcium sulfide. So we have 2, 2, 2, 2. All right, so all our charges are the same. Not going to help us out here. Let's cross out the ones they have in common. So oxygen and sulfur, which one has a smaller radius? Ugh. Oxygen does. So if oxygen has a smaller radius, it will have the larger lattice energy. That makes sense. Last statement, we have 2, 2, 2, and 1, so we don't even need to worry about radius. This has the larger charges, therefore it should have the higher radius. That makes sense. All of them are correct. And finally, we're going to go ahead and do number 10. What has the highest melting point? When it asks a question like this, it's really asking which one has the most intermolecular forces. Because the more intermolecular forces you have, the closer it's pulled together, the more heat you need to go ahead and melt it or break those bonds. If it's not evident here, this is silicon with halogens, right? So all 4 of these Lewis structures should be very, very similar except for the outside elements. And then we have silicon with hydrogen. If you don't see that, you can go ahead and draw the Lewis structures. I did just to make it a little bit more clear. So let me move this. So there's our 5 structures. So we can go through and figure out, okay, which one has the most intermolecular forces. So none of them have hydrogen bonding, otherwise we'd be able to know our answer right away. So next we're going to look for dipole-dipole. None of them have dipole-dipole. None of these structures are polar. They're all tetrahedral. Now we're going to ask ourselves, do they have London? Well, yes. Remember, everything has London, so all of these have London. We know these aren't going to have ion dipole or lattice energy. We don't have ions dissolved in something polar, and we don't have ionic compounds. So we're looking at London. Okay, since these all have London, it's kind of hard to pick which one should be the strongest intermolecular force. But remember, the larger the molecule, and we will know the largeness by molar mass, the stronger the London. So which one of these has the largest molar mass? This one. Silicon tetraiodide. So this guy right here will have the biggest intermolecular force, therefore the largest melting point.